of polynomials that are recursively defined, and we want to prove some facts about them. So whenever we have a recursive definition, induction is going to be our friend. So let's see how we can use induction for part 1. For part 1, we are trying to prove that Pn of 7 is equal to 0 mod 19 for every n. So why don't we take that as our inductive hypothesis? So our hypothesis is going to be that Pn of 7 is equal to 0 mod 19, right? Okay. So, well, we have to check the base cases, right? Here we have two different base cases, P0 and P1, because our recursive definition is P of n is defined in terms of the previous two polynomials. So we have to have two base cases. So P0 of 7 is equal to, well, from here we know that P0 of x is equal to x plus 12, so it's equal to 7 plus 12, which is 19, which is 0 mod 19, right? What about P1? We have P1 of 7 is equal to x squared minus 5x plus 5, where x is equal to 7, so it's going to be 7 squared minus 5 times 7 plus 5, which is going to be equal to 49 minus 35 plus 5, which itself is going to be equal to 19, which is again 0 mod 19, right? So we have checked our base cases. Now let's go to the inductive step. So we are using the strong form of induction, which means that you're allowed to assume that for every m less than or equal to n, you have proved your inductive hypothesis, which is that Pm of 7 is equal to 0 mod 19. And then, using this assumption, you are to prove that the inductive hypothesis holds for n plus 1. So let's write down the definition for n plus 1. What is Pn plus 1 of 7? Well, from this definition, we know how to write Pn plus 1 of x. Well, we can just plug in x equals 7 and get this formula. Pn plus 1 of 7 is equal to 7 times Pn minus 1 of 7 minus Pn of 7. Now from our inductive assumption, we know that Pn minus 1 of 7 and Pn of 7 are both equal to 0 mod 19. So if we're working mod 19, we can write this as 7 times 0 minus 0 mod 19, right? But then 7 times 0 minus 0 is just 0. Okay, that completes our induction. So let's go to part 2. So first of all, what do we know about polynomials? How many roots can a polynomial of degree d have? When you're working mod q, you learned in the class that a polynomial p of degree d can have at most d roots, right? This is, of course, if p is not equal to the 0 polynomial, right? Okay, the polynomial we are interested in is P 2013, right? P sub 2013 is not equal to the 0 polynomial. Why? Because P 2013 of some number x is not equal to 0 mod q, right? So P is not equal to 0. So if we find its degree, if we find an upper bound on the degree of P sub 2013, then that upper bound is going to work for the number of roots it has. So we are trying to find an upper bound of the form 2013, okay? Well, if you write out the first few polynomials, you see that P0 has degree 1, P1 has degree 2, but then P2 has degree 1, right? So this breaks a pattern. Before that, we had P of n had degree n plus 1, but then P of 2 has degree 1 less than its index, right? So let's try to prove that P of n has degree at most n. Of course, this statement is not true for n equals 0 and 1, right? So we have to adjust our statement to P of n has degree at most n for n bigger than or equal to, let's say, 2, okay? So how are we going to prove this? Again, we use induction. So in this case, our base cases are not going to be 0 and 1, but are going to be 2 and 3, right? Okay, P2 of x equals 17x minus 5, which has degree 1, and the degree is less than or equal to 2, right? So our inductive hypothesis holds for 2. What about 3? P3 of x is equal to x cubed minus 5 times x squared minus 12x plus 5, which has degree 3. So here we have degree of P3 is less than or equal to 3. So our inductive hypothesis holds for both 2 and 3, right? So now let's go to the inductive step. So we are assuming that for every m less than or equal to n, degree of P of m is less than or equal to m. Of course, m has to be bigger than or equal to 2. Okay, so what do we know about Pn? What do we know about Pn plus 1? Well, we know that P of n plus 1 of x is equal to x times P of n minus 1 of x minus P of n of x, right? Okay, what is the degree of Pn minus 1? Well, it can have a degree at most n minus 1, right? When you multiply it by x, it can have degree at most n, right? So this part has degree at most n. What about this part? This part also has degree at most n. Okay, when you add or subtract two polynomials of degree at most n, you get a polynomial of degree at most n. Okay, so we have seen that we have 2 degree n polynomials here. The sum or the difference between polynomials of degree n is at most n. So we got that degree of P of n plus 1 is less than or equal to n, which itself is less than or equal to n plus 1, right? So we have proved our inductive assumption. So the degree of P of n is less than or equal to n for any n bigger than or equal to 2. So in particular, this says that degree of P sub 2013 is less than or equal to 2013, which proves our claim. P 2013 can have at most 2013 roots.